Yield lines, special cases. This video deals with square slabs with one point support and two simply supported edges. This is a rectangular slab with one point support and two adjacent edges with simply support, who are simply supported. It's loaded by a uniform distributed load Q. We will start to look for the yield lines to determine the maximum bending moments. We know that we've first to look at the axis of rotation. So where the slab is supported as an axis of rotation, and here it's also an axis of rotation. But this point support, there is also an axis of rotation, but it can go in any direction. So this direction is not fixed. But because of symmetry, due symmetry around this axis, we know that the optimum is 45 degrees. This is because the support of the slab is also symmetric around this axis. The yield lines are somewhere starting at the intersection of two rotation axes with a certain angle, which is alpha, the same here. This angle is the same as this angle because of the symmetry. And this is the third line, but this angle is known because this is 45 degrees because of the symmetry around this axis. So alpha is not known because there's no symmetry around this axis, around this. Alpha is not known. We know that this is the same as this because of the symmetry around this. And this is the angle beta, but we know that beta is equal to, because this is 90 degrees, so, and this beta is equal to this, so we know beta is 45 degrees because of the symmetry. And the same happens here. This angle is also 45 degrees. The yield line starts at the cross section of the rotation axes. So this is one yield line, this is the second. The yield line stops at the edge of the slab, and this is the third yield line. So the angle gamma is 45 degrees because of the symmetry. The parameter for optimization is, of course, alpha. And to achieve that, we take the tangents of alpha and call it x. So the optimization parameter now is x, which is the tangents of this angle. We know that alpha must be, of course, between 0 and 45 degrees, or it means that the limits of alpha where is or the limits of alpha induces a limit for x, which is between 0 and 1. This is the range where we can optimize function to achieve a maximum bending moment m. We have some relations in this triangle, for instance. We got lambda plus 45 degrees plus alpha is in total of 180 degrees. So we have this expression, and lambda is expressed in function of alpha. Around this, we have the total is 360 degrees. We know what lambda is, so mu is equal to this expression. So we are busy to express everything which is situated here in function of alpha. A1, of course, A1, simple, it's A times the tangents of alpha, so it's A times X. And A2, well, it's just A minus A1, it gives you A2. H1, we use here the tangents rule for H1, it means, or the cotangents rule, means it is H1 is equal to the base of this triangle, which is 2a, divided by the summation of the cotangents of this angle and the cotangents of this angle, which gives you, expressed in x, this value. We do the same for H2, and we use this large triangle. We use the cotangent's rule for it. And S1, we can calculate directly. S1 this, yeah, of course, S1 is square root of 2 times A. S2, we can also calculate it directly, and the same for S3. So now we have all the important parameters to calculate E or D for the maximum bending moment is expressed in one parameter, which we are going to optimize. The work done by the external forces, but now we calculate it and we take E over delta Q. When we look at the total picture, it can be very difficult to calculate the mean deflection of a piece like this or a portion of the concrete like that to calculate the mean deflection when this is delta and this is a portion of delta. But we can do it in a more easier way by seeing that the whole picture is in fact a summation of triangles. You got this triangle, and you got this one, and you got the big triangle there. So everything is a summation of triangles. So that's why we take delta over 3 as the mean deflection, delta over 3. And now we consider this triangle, for instance, which is the contribution of the large triangle minus this portion which is not there. So for instance, for here we have H1 times 2A divided by 2 multiplied by the angle of rotation, which is delta over H1, which is this term. But we have to subtract this portion outside the slab. So we have to subtract A1 times A divided by 2 multiplied by the maximum deflection here, which is of course A1 divided by H1. And that's this term. We got it 2 times because this triangle is equal to this triangle. And then we are left with the larger triangle, which means that to calculate it, that is H2 times 2 times S1 divided by 2. And then we subtract what's outside the slab, which is S2 times S1 divided by 2 multiplied by S2 divided by H3, and we got that 2 times. So we can now put in the different values, the different values, and express everything in function of x, and you got this simplified expression. Now we can calculate the work done by the internal forces. It's d over m delta. And we start, for instance, with this portion, this bending moment of this plastic bending moments projected on this axis of rotation. So the total length is 2 times S2 divided by the, or multiplied by the angle of rotation, which is 1 or delta divided by H2. So that's this term. And on the other side, we have this yield line projected so this axis on this axis. So it's 8A times delta over H1, but we got that twice because this is the same. We again express it in function of x and substituting H1 and H2, and we got this expression. So the bending moment is a function of x, is a function of the tangents of this angle alpha, and is given by this expression. We can plot this expression mx in function of x, which is tangents alpha. We know that x should be between 0 and 1, and between 0 and 45 degrees. As a scale factor, we use q8 squared equals 200, otherwise you cannot plot the bending moment. So we just assume that q8 squared is 100, and then you got this nice expression of this. You see that there's clearly an optimum, so we can calculate the optimum. We take the first derivative equal to 0, and we find that this is 0 for x max equals to 0.6. And we fill in 0.6 in this equation, and we find that the maximum bending moment is q8 squared times 3/32. And that alpha with this x, when the tangents of alpha is 3/5, or when the tangents of alpha is 0.6, it means alpha is 31 degrees. So you can see clearly on this graph that for x equal to 0.6, the maximum bending moment here is something like 9.5 times 100. Using optimization of the angles, we see that the angle that this makes here, like that, this angle of this and the angle of that, is 31 degrees. And that the maximum bending moment is given by q8 squared over 10.67. When you use the 30, 45, 60 rule, it means that because this is simply supported and this is simply supported, then you take 45 degrees, which is the same as here because of the symmetry, but this is because of the rule. Then on this side, when you have an axis of rotation like this and an axis of rotation like that, then you should take the half of it. So that means alpha is the half of 45 degrees. You end up with this position of the yield lines. And the bending moment that you calculate with this kind of yield line is then q8 squared over 11.2. So you see that the bending moment is underestimated by 5% when you are using your 30, 45, 60 rule in this case. And you see also that the load that this point support have is bigger in the 30, 45, 60 rule compared with the load in the optimization.